Hello everyone, my name is Rohit Singhal and we were discussing about the topic hydrocarbons. We were recently discussing about the aromatic hydrocarbons. We have discussed about its what are aromatic hydrocarbons. Then we discussed towards why they are different from the normal alkenes. The extra stability we have discussed, the resonance we have discussed. Then we have discussed the criteria for the aromaticity, the Huckel rule. Then we moved on towards the normal things about the aromatic hydrocarbon, that it was discussed the synthetic procedures of the laboratory of benzene. We discussed 2-3 process to synthesize a benzene in laboratory. Then we started moving towards the physical properties of it. Physical properties I have discussed that aromatic hydrocarbons normally they are non-polar in nature. That's why insoluble in water and soluble in organic solvents. Then I have discussed about its state. Normally they are solid in nature. We know a basic example of these aromatic hydrocarbons, that is naphthalene. We use in our toilets and such things to remove the foul smell. Then I have discussed more towards the chemical properties of it. Chemical properties I have discussed ki unlike alkenes normally undergo, we have seen that the addition reactions, whereas this benzene molecule don't undergo this addition reaction, but it undergoes the substitution reaction. Why is it so? Because if benzene will undergo the addition reaction, it will lose its aromaticity, and that any molecule will not like to lose aromaticity, as the aromaticity directly means losing the stability. So that is why these aromatic compounds normally undergo the substitution reaction instead of the addition reactions. Substitution reaction, then we started discussing about the substitution reactions. I have first discussed the general mechanism of the substitution reaction. Benzene rings are the electron rich in nature, contain C double bond C. That is why they normally undergo the electrophilic substitution reaction. Electrophilic substitution reaction means electrophile will attack. Electrophile means electron deficient species. Okay, we have discussed nitration, sulfonation, Friedel-Crafts alkylation, acylation, halogenation. We have discussed about the general mechanism of it. 3 general steps are involved in general mechanism. It first one is generation of electrophile. Each and every electrophilic substitution reactions have different electrophile, which can be generated by using different catalyst and suitable reagents. For example, nitration, we have used concentrated nitric acid and concentrated sulfuric acid and generated the electrophile NO2 plus. Then we have sulfonation reaction, where concentrated H2SO4 is used and the electrophile was SO3H, not SO3 positive, the electrophile is SO3H. Then we halogenation reaction, X plus is actually the halogenation reaction, the electrophile is being produced. Then in Friedel-Crafts alkylation, R plus, that means alkyl carbocation, and Friedel-Crafts acylation, acyl carbocation, that is RC double bond O positive. These carbocations were generated as the electrophile. Then the second step was the attack of the electrophile, or we can say the formation of carbocation as the intermediate. A carbocation was formed, that means a sigma complex was formed from the aromatic compound. We moved towards the non-aromatic compound. Then we discussed this thing, that why this aromatic compound is losing its stability, why this is going under this reaction. That means there should be something else that is stabilizing this sigma complex. So what we have seen, that there is resonance happening in the ring that is stabilizing the sigma complex. The third one is gain of aromaticity. Then again the removal of proton happens, and the compound regain its aromaticity to back form, and a substitute product gets formed. Okay. So these were the 3 steps, 3 basic steps. The general mechanism we have discussed of this electrophilic substitution reaction. Few things I have discussed about Friedel-Crafts reaction. Friedel-Crafts reaction, alkylation, acylation. There are few differences between those two. Friedel-Crafts alkylation, alkyl carbocation is formed, and Friedel-Crafts acylation, acyl carbocation is formed. Friedel-Crafts alkylation, due to formation of alkyl carbocation, it can undergo the rearrangement, whereas the acyl carbocation do not undergo any rearrangement. That is why if you remember, I have shown you an example of reacting with propane chloride, and it instead of showing propane benzene, it show isopropyl benzene. It means in generation of carbocation in the first step, it actually rearranges itself. If normally CH3CH propane chloride is used, carbocation is of 1 degree, but it rearranges to give the 2nd degree carbocation, and the most stable carbocation is used while reacting with the benzene. So benzene reacts with the 2nd degree carbocation to give isopropyl benzene instead of giving the normal propyl benzene. Okay. Acylation on other hand do not undergo any rearrangement, and it normally gives whatever the expected product is the real product we obtain. The other thing is then we have discussed the directing groups, ortho directing groups, ortho and paradirecting groups that are called the activating groups and the deactivating groups. Activating groups, I told you that one which show the plus R and plus I effect, that means which gives the electron density towards the benzene ring, and it increases its tendency to further undergo electrophilic substitution reaction. Whereas deactivating groups are those which withdraws the electron density from the ring, and it decreases the tendency of the ring to go towards the electrophilic substitution reaction. What happens in activating groups is, activating groups increases the electron density and ortho and para position by imparting a negative charge on them during the resonating structures, and due to the imposition of negative charge on ortho and para positions, the incoming electrophile will go towards the ortho and para position, as they have the more electron density in presence of activating groups. Whereas in deactivating groups, it withdraws the electron density from the benzene ring and imparts a positive charge on ortho and para position, which in turn obviously will increase the electron density and meta position. Therefore, an incoming electrophile in case of a deactivating group will go over the meta position instead of ortho and para positions. Okay. So, this we have shown. Deactivating groups are normally which show minus R and minus I effect. Examples of activating groups are NH2, OH, OCH3. Examples of deactivating groups are NO2 or COCH3, that is acyl group, sorry. So these are the examples of it. One special case we have discussed is of the halogens, that halogen shows minus I effect, but due to the presence of lone pair, it also shows plus R effect. Now there was a question whether it will be ortho and para directing group or meta directing group. That means which effect will have a higher say in presence of determining the direction of the incoming electrophile, whether inductive effect or the resonance effect. Then I told you one thing, that the incoming position of the electrophile is being determined by the resonance effect, not by the inductive effect. Resonance effect will determine whether the incoming electrophile will go over the ortho and para position or meta position. So in case of halogens, it's why because of it they are showing the plus R effect, the incoming electrophile will go over the ortho and para positions. But it also shows the minus effect, and the inductive effect will have no control over the position of the incoming electrophile. It can determine the rate of the reaction. Normally the halogenated product, or we can say halogen benzene, normally do not undergo very easily the substitution reaction, because minus I effect, although it increases the electron density, but it also withdrawing the electron density from the ring. So that is why these halogens are called mild activating groups, and other like NH2 or we can say OCH3 are great activating groups, and they increases the tendency as well as they direct the incoming electrophile towards the ortho and para positions. Do remember this direction I am telling you about the electrophile. In case of nucleophile, the things will be reversed, as the nucleophile will prefer to go over the position which is electron deficient, and electrophile will tend to go over the position which is electron rich. So this you have to keep in mind. So now we have discussed the this ortho directing groups and para directing groups. One thing is left is just the general properties of this is toxicity. Okay, not much left with in this hydrocarbons, aromatic hydrocarbons is what happens normally is that when there are more than 2 benzene rings are attached, benzene is fine when there are more than 2 benzene rings are attached. Okay, when there are more than 2 benzene rings are attached, this is an example. This is called benzaanthracene. Okay. These are the examples that have been mentioned in the NCERT book. Okay. So normally what happens is when there are more than two benzene rings fused together, more than two benzene rings fused together, they are carcinogenic in nature or they are toxic. Okay. These are carcinogenic in nature when more than carcinogenic means cancer causing. Okay. This kind of hydrocarbons, aromatic hydrocarbons, in where more than one we can say more than two benzene rings are fused together, these kind of hydrocarbons are normally carcinogenic in nature. These are toxic to our human health. So what actually happens is how these are formed. These are formed by the okay. So what actually happens is how these are produced. These are actually produced by the incomplete combustion of the organic materials like tobacco. Smokes the tobacco, it do not undergo the complete combustion. It undergoes the incomplete combustion, and due to various kind of gases, or we can say harmful gas or harmful smoke, and that smoke contains this harmful kind of carcinogenic toxic materials to human health. That's why this tobacco and all things are injurious to health. So these things actually go into our human body, and it does a several biochemical reaction. These are undergoes several biochemical reactions. This damage our DNA molecule and will do certain something this carcinogenic or several biochemical reactions which will not be suitable to one's body health. So that's why these are carcinogenic, and more than two benzene rings fused together, normally they are toxic for the human behavior or human health. Okay. So with this I have finished the aromatic hydrocarbons too. We have discussed with the alkanes, alkynes, aromatic hydrocarbons, all we have discussed, and with this thing I have finished this topic of hydrocarbons. Okay, thank you so much.